Okay, right. Well, so yeah, welcome to everyone. Welcome in particular, obviously, to Anton and Jan Lucas, who will be giving us an interesting talk today. And Scott's also joining us, so we're pleased to welcome him. Yeah, so the basic plan, I mean, I'll just explain that I've been going through the paper, Scott, reasonably carefully that we wrote until, well, the period just before it gets into the actual finite dimensional distributional convergence of the scale processes to fractional Brownian motion, which was this sort of backwards from infinity martingale difference argument, which I a little bit skimmed over, but gave some impression of the proof of that. And obviously a couple of weeks ago, Jan Lucas and Anton were in touch with us regarding perhaps a tiny little bit of a discrepancy that has cropped up in the later part of the proof. So we agreed a couple of weeks ago to hand over to them for their presentation today, which will in some sense treat the end of the topic, although it is a topic which I think is actually rather good for open problems. We've been discussing some open problems about if you take a simple random walk and it kind of on the y-axis you put plus or minus 1 cookies that are there consistently and collect them, if you see what I mean, and add up along your process the increments you get. Adam and Jake have been looking at this process, which has some similarities and differences to, it has a kind of 3/4 exponent, so one might expect it to give fractional Brownian motion with a parameter 3/4, but in fact that's not quite the behavior it has because it fails to be Gaussian. So anyway, there's various open problems we could discuss, so perhaps when Jan Lucas and Anton finish, we can, well, obviously there may be some debate arising from their talk, but there's also some, I think, nice open problems. For example, there's a voter model based problem, and I think that would lead into nicely the question of whether one could have a natural dynamics that leaves the fractional Brownian motion limit kind of invariant that could come out of either the model Scott and I introduced, or you could do a voter model variant that might be slightly more natural from a dynamic point of view. So those might be directions we could talk about as we sort of bring this topic to a conclusion in the next week or so. So anyway, that's just some background. So I'll just basically hand over to Jan Lucas and Anton at this stage for their presentation. They're very kindly prepared.
So thank you so much, Alan. We are very happy to be with you. This is a very nice occasion. And as we already know, we started looking into this very nice paper of yours and found this little difficulty in lemma 4.1, which we will come to in the course of this lecture. But the most important thing is that the lemma is true as it stands, and it can be obtained by a sort of detour, which gives some insights also into some general theory. And we thought it's just nice to build this in at this place. And so in fact, our joint presentation, we will change, we will hand over this pencil at one time, is consisting of 5 parts. It's a drama in 5, or a play in 5 acts. And the first 2 of them deal with what's now on that slide, a conclusion of the proof of the main theorem of the paper, with the subtitle From Finite Dimensional to Locally Uniform Convergence in Distribution. That's in fact the first part. The second part will then be these joint couplings, the couplings which we learned already in Alan's course about jointly in all times. And the third part will be a little glimpse on lemma 4.1, namely what the difficulty is. Actually, this can be done quickly. It's just a little zoom into where is the difficulty in the original proof of yours, and then part 4 will be another proof of this lemma 4.1, again building on some general theory, and part 5 will be an outlook to a paper by Jochen Blatt and others, which appeared in the same year as yours, and which also, actually that's the topic of Gianluca's master thesis, and it will give us an opportunity to discuss a little bit with you also convergence towards fractional Brownian motion in that population genetic setup. But that's not, that's a little bit also still work in progress, and it will be at the end of the talk. Okay, now part one. Part one is has this title, and let me just recall. Where we are building on is your proposition 3, and this is the finite dimensional convergence of the processes Sn. These were the linearly interpolated rescalings. You remember? I mean, these were these things which were doing these things, of course, with these correlations, right? The long-term correlations, and then this converges for all finite time points, right? This converges towards the distribution of fractional Brownian motion. That's what we have. And now we want to go from these finite dimensional distributions to a convergence with respect to the supremum norm, right? So we have now random variables, right, which take their values in the continuous paths from 0t to the reals and endowed with the subnorm or the L infinity norm, if you like, but on that interval 0t, right? That's the task. And now a very short reminder to, well, actually, calculus or a real analysis. What can go wrong on the way from pointwise to uniform convergence, right? That's just a, and here is a very elementary example, right? If you have a sine function which you squeeze into narrow and narrower point intervals, right? Then of course these functions, as n tends to infinity, they are squeezed into narrow and narrower bits. That converges pointwise to 0, but not uniformly, right? So question, I mean, what's going wrong here? Well, it's losing more and more of its modulus of continuity. The modulus of continuity is going worse and worse. And this is this memo from real analysis for a sequence of continuous functions which converges pointwise, right? The missing bit to uniform convergence is a common modulus of continuity. A common modulus of continuity, which means we have a function omega of epsilon, which converges to 0 as epsilon tends to 0, such that we have a uniformity in the continuity, right? When the arguments are closer than this omega of epsilon, then the function values are closer than epsilon and uniformly in n, right? And that's the missing bit. And in fact, there is this nice theorem by, come on. One thing, and now I'm learning with this nice tool here. There is Ascoli-Arzellas theorem, right? Which is a theorem from real analysis, which says that relative compactness in uniform convergence on this space, right, is equivalent to uniform boundedness plus a common modulus of continuity, right? And relative compactness means that every subsequence has a convergent subsequence, right? When you have a sequence, saying that this sequence is relatively compact, well, every subsequence has a convergent subsequence, and that will help us, right? Of course, the corollary of this real analysis thing, which is a sort of warm-up for what will follow, is this fact which I claimed, right? If we have a pointwise convergent sequence of continuous functions, which has a common modulus of continuity, then it converges uniformly, right? Now let's do a fun proof of this. This is here is the proof, right? The assumptions that we have here a common modulus of continuity, right? These assumptions imply also that Yn is uniformly bounded. That's already one bit of the Ascoli-Arcelà theorem, we have this common modulus of continuity by assumption. That's the other bit of the Ascoli-Arcelà theorem, and therefore Yn is relatively compact, right? Now assume this sequence would not converge uniformly. Then it would stay away, right? At least a subsequence of it would stay away in the subdistance from the Y. And by relative compactness, this sequence which stays away from the Y has a subsequence, right? Which then would converge because of relative compactness, right? But now we have finite dimensional. We have pointwise convergence. That's the assumption. We have pointwise convergence, and that's a contradiction, right? Because pointwise convergence determines the limit. That's a contradiction, right? So far, this is a pure warm-up from real analysis, and now we will switch to probability, right? And let me say, whenever you interrupt with a question, this is highly welcome, right? I'm happy about questions that makes the thing even more familiar, and it's so nice to be so close with this medium. Okay, now the strategy of your Allen and Scott's proof of lemma 4.1 was a attack towards the modulus of continuity, right? Actually, you had your SNs. These were the candidates you wanted to show convergence of. You knew that this is finite dimensionally convergent, so in the sense of finite dimensional distributions. And so this lemma 4.1 says or claims that the maximum of what is happening in between 0 and 1 of these rescaled interpolated paths cannot be terribly big in distribution, right? Actually, looking at this, if you set the log epsilon to the -1 squared, right? If you set this u, then the epsilon becomes e to the -u squared. And so this lemma says the maximum of these rescaled random walks in between 0 and 1, right, uniformly in N has Gaussian tails, right? So it has no more than Gaussian tails, right? That's what you are claiming in this lemma. And indeed, this assertion does help for obtaining what we will soon call tightness. I mean, that's called tightness, and that's the next concept. Right, that's what I said here, right? This lemma can be seen as a direct attack on a modulus of continuity that is common for the Sn with high probability, right? And this would be good for applying the first of Billingsley's tightness criteria stated below. And here is first a way to circumvent a direct proof, which has this little difficulty we will come to, by a detour, right, using some general theory on random variables that are valued in the continuous paths and endowed with a subdistance. And the nice thing is, finally, we will come back to lemma 4.1 and we'll have a proof of lemma 4.1, right? Even with a beta constant than 50. And so the keyword, which I already mentioned, and which is worth to lose a few words on, is tightness, right? Tightness. And this is equivalent, as we will see, that's another little theorem by a nice guy in Russia, right? Prohorov. Tightness is equivalent to relative compactness of a sequence of random variables in the sense of distributional convergence. And here is this bit which is now even more abstract, because it deals with random variables in a complete separable metric space. I mean, complete separable metric spaces are the nice playgrounds for us, right? I mean, because there we have nice disintegrations and all kinds of benign behavior. And Prohorov's theorem says that relative compactness of a sequence of random variables which takes values in a complete separable metric space is equivalent to, and that's now very much reminiscent of the good old Heine-Borel and Bolzano-Weierstrass. I mean, these things for sequences, right? And here we have sequences of random variables, and we cannot say they are all squeezed into a compact set, right? Or into a relatively compact set. But we can say this, what is here in blue, right? They are all falling into one compact set with high probability, right? That's the blue statement. For all epsilon, there exists a compact set such that all these random variables fall into this compact set with high probability, right? And the sequence with this property is called tight. And now there is a marriage of Prohorov and Ascoli-Arcela, right? Because Prohorov says, look for compact sets where you fall in with two with high probability, right? And Ascoli-Arcela tells us how these compact sets or relatively compact sets look like in the topology we are after, namely the supremum distance, right? And And actually what Billingsley did is just writing this marriage down in a sense, right? So this is one of the tightness criteria one finds in Billingsley's book on convergence of random variables. And it reads like this, right? And actually now these are all good old friends. If we look, at first sight, such a theorem, I speak of my own experience, right? It's appalling, right? Because one thinks, what's that here, right? But if we like the good old Romans, divide et impera, right? Or conquer, divide and conquer and reign. So what does this say? We have a sequence of random variables taking their values in the continuous paths. Then this sequence is tight, is relatively compact in the convergence in distribution, if and only if these two conditions hold. First, all these random variables are uniformly bounded in zero with a high probability. And second, with a high probability, they have a common modulus of continuity. That's the message of this theorem. And we made sure that having your theorem, having your lemma 4.1, this lemma 4.1, which I stated a couple of minutes ago on the slides, right? Having this lemma at hand, one can apply this Billingsley lemma, and then one does have tightness of the rescaled paths Sn, and therefore, because we have your proposition 3, we are done, right? But there is another way to circumvent lemma 4.1, and this is another criterion in the Billingsley book, which has a little twist, right? If you look at this criterion of Billingsley, what we have is we have a sequence of continuous paths, yn, and nothing else, right? And this is a criterion in terms of the yn, and nothing else. But if one knows more, right? Namely, if one knows that one has a candidate y to which the yn converge in the sense of finite dimensional distributions, as is the case with the SNs, right? Because we know that the SNs converge to the S alpha plus 1/2 to this fractional Brownian motion on every, they converge to this in finite dimensional distributions. Then there is a simpler criterion that is sufficient for tightness. And this is an interesting thing, right? If one has a candidate where one knows finite dimensional distribution 2, then by some cute tricks which are done in this Billingsley book, one obtains a very nice criterion. And here I hand over to Jan Lucas, and he will present this criterion and apply it to our situation.
Yeah, so, okay, we have our FDD limit, and okay, let yn be a sequence of our random variables, yes, and we have finite dimensional distribution convergence, so at least to a variable y. And now the question is, okay, when is our sequence tied? And the sequence is tied if for all time points s, t, and u, okay, smaller than t, and some gamma greater than 1, and a non-decreasing continuous function f on 0 to t, we have that the expectation of the product of the increments of yn between t and s and between u and t is bounded by the difference of f between u and s to the power of some gamma, okay? So how do we apply that? Okay, so Thiemann had a nice way to apply it, and he had somehow another random walk and showed convergence to fractional Brownian motion. So the main work is done by Allen and Scott because of dilemma 3.1. The nasty calculation we did last week is the key. So
not nasty calculation, beautiful calculation.
okay, the longer calculation.
The long calculation.
So what is implied by lemma 3.1? It's implied there exists a constant C1 that the variance of Sn is smaller than C1 times n to the power of 2 alpha plus 1 times L of n to the power of -2. Okay? So let's fix some time points S, T, and U. And on the jitter with mesh size 1 divided by n, we just approximate S, T, and U discrete. So take some J, and so that J divided by n is smaller than S and J plus 1 divided by n is greater than S. And do the same for T and U.
Maybe you make a little sketch.
Yes, maybe I make a sketch. So what we have is 0 to T, we have S, T, and U. And what we know is J divided by N, somehow here. It could be S. J plus 1 divided by N is greater than S. Same for K divided by N. And K plus 1 divided by N. And of course, the same for U. So what can happen now? There are two cases. The first, maybe we just first look what linear interpolation gives us, because that makes things much easier. So we have our increments Sn from of t minus Sn of s, okay, divided by our rescaling. And what linear interpolation gives us, it's just a sum over the xm. And yeah, some factors times the first and the last one comes from linear interpolation. So what we can do now is the following. Using lemma 3.1 and that L is slowly varying. Okay, the first bound is that. It's given by lemma 3.1 and the fact that we can interpolate linearly, and of course xj plus 1, xk plus 1, they are all plus minus 1. These are not greater than 1. Okay, that gives us the first inequality. The second one is not harder, because for the second one, we have the variance of sk minus j. Okay, we have lemma 3.1, we apply it. The next one, there we use that L is slowly varying, so otherwise we couldn't get this 5 out. One can think of a constant L and everything is fine. So if you just want to think about a constant L, yeah, do that. Okay, what we get is that the variance of this increment is smaller than C3 times k minus j divided by n to the power of 2 alpha plus 1 and something with a slowly varying function. Remember, what was k minus j? K is that, j is that. So it's the left side discrete approximation of s and t. Okay, you can do that also for u and t. I think all of you believe that. So what we have to do now to apply the Billingsley criteria is to bound the expectation of the product of these increments. The first thing that can happen is that L is smaller or equal than j plus 1. then the difference between u and t, or the difference between t minus s, they are smaller than 2 divided by n. And so there's only one or maximum 2 increments we really have. The rest is linear approximation. Okay, so this is small, that's bigger than both of them. Okay, 1 plus a is smaller than 2. So this inequality obviously holds.
So this is the case where all of them are really close,
Yes.
right? Maybe you can.
Yes, I make another.
Picture.
So what we have is j divided by n. There we have s, and L is smaller than j plus 1. So something that is left of u is here. Here's some value by 1. So the 3 points in time are very, very close. Okay, for n large enough, one has that L of n is smaller than n to the power of alpha. Yeah, you can argument.
Because it's slowly varying.
Yes, then the other argument is to just look at the definition of mu. Okay, so what does linear interpolation give us? Between u and t, there are maximal 2 increments, and between t minus s also. Okay, so we have a rescaling in both of them and the maximum increments they can do. Between u and t, it can go up 2 divided by n, or it can go down. Okay, so we can bound that. We have a bound on that product, and yes, the bound on L implies this inequality. So what we are left with is our c tilde squared times 1 divided by n times u minus s to 1 to the power of 1 plus 2 alpha. Okay, this 1 through n is small, so just give it away. And what we are left with is some constant c4 times u minus this constant times s to the power of 1 plus 2 alpha for some constant. And that looks like the criteria we need. Yes? I just go back a few slides. Yes. So we have a function, a difference f of u and f of s, and gamma is obviously 1 plus 2 alpha.
And f is linear, right? It's
yes, f is linear.
Constant times the identity here.
Yes.
Right?
And we now take a closer look what happens when L is greater than j plus 1. So when these points don't lie together.
Maybe here, just to say a little anecdote, if you have looked into the notes, one or the other of you, then you will see that at that point the argument is just one line, right? It says one of the two factors must be 0. When they are so close together, one of the two factors must be 0. And this is because we copied Sotinen, because Sotinen at that point works, or in his entire paper, he works with Gauss brackets, right? And therefore with stepwise constant approximations, not with linear interpolations, but with stepwise constant approximations. And then, of course, if you squeeze the arguments close together, then two of them must lie in the same little grid interval and have the same function value, right? And this was putting us into excitement in the last hour before today's convention, because we realized that only an hour ago, right? And then we were both a little bit, but Jan Lucas was able to repair this even here in the slides, and so maybe this is a nice complement to what we wrote in the notes, right? But now comes the more important, more interesting part. When you have those arguments further apart.
Yes, maybe just one other word about Sotinen. It's somehow confusing that he uses these brackets L floor and R floor, and then uses a theorem from Billingsley for continuous
Right.
processes.
Right. The compactness criterion, which we are presenting here, this second criterion of Billingsley, is formulated for continuous functions, right? My feeling is that applying it to a sequence of stepwise constant functions whose jump size converges to 0 doesn't give much harm, right? But it has to be checked, right? So anyway, okay.
Maybe it's now treated with some care, and we are happy with that. Okay, now look at the interesting case. L is greater than j plus 1. These points are not so nearby, they are somehow far away. Okay, we have an estimate on the variance and Cauchy-Schwarz. Okay, first we just use Cauchy-Schwarz to bound our product. Okay, what we have is a product of variances and the square root of it. Okay, we have a bound on the variances, and the biggest it can get is L minus J divided by N to the power of 2 alpha plus 1. And I believe all of you see that it looks nearly the same as this one. C4 times U minus C4 times S. Okay, what we have now is 2C3 for some other constant C3 times 2 times U minus S to the power of 2 alpha plus 1. So it's the same gamma and nearly the same linear function. What we do now is just take the max of C3 and C4 and multiply it by 4 and use that linear function. The bounds still hold. And what we have is that we bounded the product, the expectation of the product of those increments by the difference of a linear function to the power of something greater than 1. And that means we can apply Billingsley's theorem 15.6.
Right.
And okay, what we have proved now is the following, proposition A. For all t greater than 0, the sequence of the random variables s and t only on 0 to t, okay, converges in distribution in the room of continuous function on 0 to t equipped with a subnorm for our fractional Brownian motion on 0 to t. I believe everyone is happy with that. We just used some general theory here and the fact that we interpolate linearly.
Right, and the crucial thing, maybe we come back to this, is this estimate on the variances, right? I mean, yes. Here the variance of the increment, right? You have to have a bound on this variance of the increment, and of course, since this is all homogeneous, it's precisely the lemma 3-1 thing which goes in here, right?
Yeah. So really the main work is done by lemma 3-1. The other things are somehow general theory. And
hello.
Hello.
Yeah.
So
that was the
security. Okay, what we have now is a statement for each t separately. But what theorem 1.1 claims is the existence of a sequence of couplings that works jointly for all t in time. So we don't want a time-dependent sequence of couplings. And yes, that will be settled in part 2. And I remember correctly, that's the part where I should give you the upper.
I will take over again. So part 2 is already much smoother, right? It's again a bit of general theory, which is nice to state here. And this already popped up in your course, Alan, namely this thing, how can we relate close by distributions to close by random variables, right? This idea of the coupling, right? And let me state proposition B, which for us also was quite instructive. Actually, I learned quite a bit here because part of it was just refreshment of what I had learned long time ago, and somehow, I mean, I was not a real, I mean, all this tightness business, but then on that occasion, I I decided to look into it from really from scratch, right? With this marriage of Prohorov and Ascoli-Arcela. I mean it's quite nice. So you can say the marriage of Ascoli-Arcela and Prohorov gives Billingsley in a way, right? That's to memorize. But now we are in part 2, and here is proposition B. Again, a little bit of general nonsense, but still nice, right? Given continuous processes on the entire time axis, from 0 to infinity, a sequence yn, and given a limiting process such that we have local uniform convergence in distribution, right? Local uniform convergence in distribution. That means for all t, the sequence yn as a C0t valued sequence of random variables converges in distribution to yt. That's precisely what we have so far, right? That's what we have by proposition A. And the claim here is, then there exists a sequence of couplings Cn, which is good uniformly in T, right? So that's the claim here. This sequence of couplings makes Yn and Y close in all these spaces. Right? Okay, how to get this? How to guarantee this? Well, there are 2 parts. The first is for each T. That's just a little reminder of what came up already in the course at one place, and then simultaneous for all T. That's a little technicality. You will already maybe guess that this is a sort of diagonal argument which will come up here, right? Okay. But there is this nice general framework again, which is fun to just recall. Namely, when we have convergence in distribution or weak convergence of the laws, which is the same, right? And the space is metric space, right? Then there is a metric in the space of probability measures. And we say that the distance of mu and nu is the infimum of all deltas, such that for all a's, when we have here the a, and we make the a little bit larger to a delta, the delta enlargement, that is all points for which there exists a point in A such that the distance is not larger than delta, right? And if we have the infimum of all the deltas such that mu of A is not bigger than nu of this enlargement plus delta for all A in the Borel sigma algebra, and this should be an E actually, then this is called the Prohorov distance of mu and nu. In fact, this is a symmetric thing because you can replace A by its complement, and so although it doesn't look entirely symmetric, it's symmetric. That's the distance on the space of a metric, on the space of probability measures. And there is also a metric on the space of random variables. Namely, again, we have a metric space. And now we have two random variables taking their values in this space E. And then we take the infimum over all delta such that the probability of the distance of x and y being bigger than delta is smaller or equal to delta, right? That's a metric. It was found somewhere in the 40s of the past century, and it's called the by a person named Qi-Fan, and it's called the Qi-Fan metric in Dudley's book, for instance. And there is a very nice relationship, which let's call it the coupling lemma, which you can find in Dudley's book, for instance, with a nice in a section which has this nice title, a speaking title actually, nearby variables with nearby laws. And it says that in fact the Prohorov distance and the Qi-Fan distance are the same, right? In a well understood manner, right? When we have a complete separable metric space again, right? So that's good to know, because otherwise something may go wrong. When, for instance, you cancel the complete, something may go wrong. But for a complete separable metric space, when you have two distributions that have a Prohorov distance rho mu nu, then you can always find indeed you can realize this by a coupling, right? X and Y having these prescribed distributions, and the pair X and Y has the Qi-Fan metric exactly that, right? So and also Qi-Fan is always not smaller than Prohorov, right? So the optimal coupling is realizing exactly the Prohorov distance in terms of its Qi-Fan distance. And now we are well off, because well, okay, this says in words, this says that the Prohorov distance of two probability measures can be realized as the Qi-Fan distance of a coupling with these marginals. That's precisely what I said before. And now let's apply this to our situation, right? I mean, we have our nice proposition A, which guarantees distributional convergence for all time horizons T separately, right? And therefore we have couplings for each of those T separately, right? So, here this is formulated again in the framework of this part for a general sequence Yn of continuous processes, for which we assume that there is a limit Y such that Yn converges to Y locally uniformly in distribution. Then, because of the coupling lemma, which we just stated, for each T, there exists a sequence of couplings and a sequence epsilon n converging to 0, and the epsilon n is also depending on T, right? Such that this here holds. Well, you realize that's the Qi-Fan, right? And because we have that the Yn converges in distribution, right? The Prohorov distances converge to 0, right? So just take their Prohorov distances and realize them by Qi-Fan, right? So that's a smooth thing, a smooth corollary of the coupling lemma for each T separately, right? And now what still remains, and actually it's again something which you cannot just look into, or maybe you can, but it's not, it's could be an exercise in Billingsley, who knows, but we just try to figure this out, how to get couplings not depending on T. And there is a detail which is hidden here on the slides, which we wrote into the notes, because actually what one needs here is also a disintegration on the space of continuous functions, because we have to extend the coupling to the entire zero infinity. That's a little bit under the carpet here, but the more important thing is this diagonal argument, which I will hand over to Jan Lucas again.
Maybe in fact it's a good place here to give some credits to Alan, who inspired us to use Strassen's theorem. I believe Scott and Alan, you knew our first version where we used Skorohod's theorem, and it was the first lecture we heard by Alan, right? And then we had this phone call going to till 1 a.m. or something, and thought there must be some non-general nonsense theorem that we can use. And
yes, Skorohod would be a little bit too heavy, right? Skorohod comes up with an abstract construct that is realizing everything on one and the same probability space, but it's indeed a question on couplings, right? And we adopted your sympathy for couplings, Alan. It's a good thing, right? Okay.
So that inspired us to this version. Okay, what we have to do now is some kind of an inverse diagonal sequence argument. At first we thought, okay, just use a diagonal sequence argument and be happy. Then Anton wrote this email to me, no, that only gives a convergence about along a subsequence. I wrote something back, he wrote something to another email, and we were both really excited this evening and nearly had the same ideas when writing emails. Okay, but back to mathematics. What we do is define this n of t epsilon as the minimum of k of the case, so that for all m greater than k, epsilon m of the sequence that belongs to our t is smaller than epsilon. Okay, that's just how far we have to go, that we are always smaller than epsilon. And what we do now is define an increasing sequence, strictly increasing sequence, mn, as the maximum of mn minus 1 plus 1. Okay, we want it strictly increasing, and n of n, so the time horizon is 0 to n, and epsilon is 1 divided by n. Okay, and we take m1 is equal to n11. We are still not finished. We have to define another sequence, and that's what I would call somehow the inverse diagonal argument. You define delta n by k to the power of minus 1 for the largest k. You don't even need this for largest. It has just to be a k, so that mk is smaller than n and n is smaller or equal than mk plus 1. So just take an n between this mk and the next of the sequence of the m's. Okay, warp up that. What we have is, under the c and t's in the subnorm, only on the time horizon 0 to t, the probability that yn and y differ more than epsilon and t is smaller than epsilon and t. Okay, we defined nt epsilon as the minimum over the case, so that the sequence stays smaller than epsilon, and our increasing sequence mn and our inverse diagonal sequence delta n. Okay, what we get now is the following. CNN, so the couplings of the process yn and y for time horizon 0 to n under this probability measure, or under this coupling, probability that they differ more than delta n, remember delta n is defined through 4, is smaller or equal than delta n, right? We did nothing more than just put that together. 1 and 4, in fact. Okay, so what do we have now? Just say Cn is defined as CNN, and that does the job. Because when we take the limit n to infinity, you even get that you can send a time horizon to infinity. Just put a t there, for n large enough, that's true. So what is proved now is theorem 1.1 and even a slightly stronger version of it, I would say. Okay, and I wrote that down another time. And what we will do now, if there are no questions till now, is just a little proof with Borel-Tis of your nice lemma 4.1.
Yes.
And I think lemma 4.1 gives some insights on how the process behaves.
Right. So that is now part 3, which is going beyond the proof of theorem 1.1, right? I mean, theorem 1.1 is now the proof is now complete, because just to recall, in part 1 we proved the local uniform convergence in distribution, and in part 2 we constructed the couplings uniform for all times, right? With this diagonal argument or inverse diagonal argument, right?
You should really think about an inverse
Right.
diagonal argument.
Right.
Otherwise, you only get this convergence along a
right,
subsequence.
right, right.
Can I ask one question about a previous part?
Yes.
I don't know if this is part 1 or 2, but and I think you mentioned this and I just missed it. But the variance estimate in the paper is an estimate for 1 point, and you said somehow because there's some degree of stationarity, you can use this same result to understand the variance of an increment. Is that right?
I believe what think about is
It's here, right? Or
not
even
quite
before.
here. I believe.
Sorry, I guess it's very far back.
About,
It's this, right?
it's the last equation. Yeah, it's this and the last equation. So because of the last equation, this increment is nothing else than a sum over increment xm. And because of the stationarity, you just can think of that as sm, s of sk minus j plus 1, plus these small things times times 2 increments. Okay, so
I see.
Right. It's indeed. You see here these the increments of the Sn, right? They are sums over x's, right? Sums over x's, and these x's are the colorings of these components of the graph, right? And indeed, this is a stationary situation, right? The colorings which are obtained by the coalescing renewal processes, right? Which are the basic thing. This is a stationary situation, and so it's a Gibbs measure, which is also stationary. You don't leave the stationary realm here. Right?
So the question is just what is the difference between S and T and S and S? That's how many x's you add between time S
plus
and
a little
time T.
plus a little linear
Yes,
interpolation.
plus
I
epsilon.
see.
Right.
Oh, okay. Perfect.
Thanks for the question. Really.
Thanks.
Yeah.
Thank you.
And are there any more questions? Because this is now in fact it's a sort of good point to nail down the thing that now this is completing the proof, right, of theorem 1.1, and the rest is, please.
Yeah, so my question was very just simply, why do you need two cases? Surely this case would cover the previous one. The case where you have L is greater than J plus 1.
Okay, here is this sketch again, right?
Yes.
Was it here or earlier? I think it was earlier.
If it's a minor point, that's fine. I was just wondering why you need two cases.
Because if they are too close together, there are no new increments. It's just this linear interpolation that gives you a variance.
Right.
That's the idea.
Right.
Okay.
But it could well be that I mean, this is if you detect some flaw here, it could be. But we had some energy put in here and hope that you somehow have to. There is a good reason to distinguish these two things, right?
Okay.
Okay, thanks.
I believe the reason really is that you don't know on which increment to apply lemma 3.1. So otherwise, I think you have to look at more than two cases. But that are my thoughts an hour before our talk. So
the thing where you are close together, it's just elementary calculations by putting together these straight lines, right? And there is no probability in there. And the other thing,
the only probability is in which direction they go, but you don't care about that because you just want to bound the absolute value.
Okay, now, okay. Now here is a result which actually I did not know before, but by some accident was pushed on because of some other master thesis from statistics, and it was a nice coincidence that in these days I learned about this, and it's a statement on the maximum of, or the supremum of a Gaussian process, or more generally a Gaussian field, right? It's extremely general result, and this is no typo. It's not Emile Borel, but Christian Borel, much younger guy, and this. If you Google it, right, then it's the official name, which has been coined in some books and so on. But this T stands for three Russians: Tsirelson, Ibragimov, and Sudakov, and it says that in words. Here it's in words, right? It says that the supremum of a quite generic Gaussian field, all you need is that it has an almost sure finite supremum, right? And if you know that, then automatically the expectation of this supremum is finite, and also the supremum over the second moments is finite, and you have at most, or I mean exactly, it's not precisely Gaussian, but the tails are what one calls Gaussian tails, right? It's this probability estimate holds true, right? And you see, that's well tailored for fractional Brownian motion, because fractional Brownian motion on 0t is certainly something which has, by continuity of paths, right, a finite supremum, right? The maximum of that guy exists on 0t. And that's how we will apply it, right? In order to guarantee that the maximum of a fractional Brownian motion has Gaussian tails, right? So that we do. We choose y as the fractional Brownian motion, and then from the variance structure of the Brownian motion, we know of the fractional Brownian motion that the supremum over the second moments on 0, 1 is attained at t equals 1, and it's 1, right? So the v, which we have in the Borel-Tys inequality, let me just go back to it. The v is 1 here. And then we had some chasing in the literature in order to find what is the expected value of the maximum of fractional Brownian motion.
If you research that, be very, very careful.
Well, there is a paper in the ArXiv by big names, and they reverse it, right? It's not square root pi over 2, but
I mean, they just took the inverse or something like that.
Right.
Or even inverse and then divided by 2 or something like that, or just divided by 2.
Oh, come on! Or did we, probably we did the wrong thing here?
No, we did it right.
No, it's this damned pi over 2, which is wrong, right? No, here we did a copy and paste thing. If you look here, right,
right,
that's the correct thing. But here, this is wrong, right? So I'm sorry. It's 2 over pi, right? And that's of course a much better bound, because it's just a factor 1 over pi, right? Which is between what I just scratched out and the correct thing, which we then took into the next line correctly, right? But we missed to correct this. Sorry, but it's so this is in a paper by. It's down here, right? By 2 Turkish colleagues. Right? It's not. It's 2 Turkish colleagues, who mentioned this and gave credit to Noros in the 90s. But I just put this because the Noros reference is in some maybe difficult to obtain a journal, and this is easier to get, and it's also in the ArXiv, but probably there is also a difference between what's in the ArXiv.
Yes,
here, right?
You have to look carefully.
Yes.
There's one article in the ArXiv and one published.
And the correct thing in the ArXiv, there is still a little bit different, but this
Yes.
this is the correct thing, also consistent with the Noros, and now if we want to have this for the modulus, then we add another 2, right? And a factor 2, and now putting u as we said, right? I mean, this is the thing. Then we obtain from the Borel-Tys inequality that the probability that the maximum of the fractional Brownian motion exceeds this, right, is smaller or equal to epsilon, right? That's Borel-Tys applied to fractional Brownian motion, together with the information that the expected maximum is not larger than square root of 2 over pi, right? And now we are in a situation like Donska's theorem, right? The origin of Donska's theorem was he cared about the maximum, right? I mean, the maximum is the prototype of a continuous function on the paths between 0 and t with respect to the sup distance, right? So that's a continuous function, and we know that the maximum must converge in distribution as soon as we have the convergence in distribution with respect to the subnorm, right? That's now we are in good shape, because we take this function, right? This function is functional on the paths, and that's a bounded continuous functional on C0, 1 with respect to the subnorm, as I just said. Hence, also the maximum converges in distribution. The maximum of the rescaled random walks converges to the maximum of fractional Brownian motion by proposition A, right? And then I'm grateful, Alan, that you brought this up at one time, right? Because you said portmanteau must go in here somehow, right? And indeed, right? I at that time I had to look. It's a shame, but I had to look it up again, right? It says that the Lim sup for closed sets, right? For is fine, right? It's smaller than the probability, smaller or equal than the probability of this same event for the limit. And since we have our limit under control, that's the Borel-Tiss story, right? Then we also get this convergence here, and it's the lemma 4-1, right? With an identified constant, and with a square root of t instead of 50, right? So, and now, very brief, I don't know, I mean, this is, now we have to look, it's 7 minutes to 11, right? Maybe we should just go over this very quickly, right? I mean, because it's just, I mean, now saying here is this little technical difficulty. I mean, it's of course for the group a nice maybe chasing. I want to
we give a prize.
Right, actually, this was my idea. I gave a prize if somebody if somebody finds a way to come over this, right? Difficulty. Here is a very brief browsing over the thing, right? Where is
I'm curious to hear about it, so I wouldn't.
Oh, sure,
I mean,
sure.
people
Right.
people are at liberty to drop out if they've got other things to do.
Right.
I'm a bit curious.
And we can also maybe go over the blood stuff after the end of the recording or whatever, right? Anyway, then we do this quietly. That's nice. So here we put p equal to 1/2 for simplicity in order to have a little less to write, right? Then just remember the notation. S0, S1, ... which was our S subscript n, right? Is the centered Polias-Urn random walk, right? That's the initial thing built on the coloring on the axis. And now, as you did in the paper, abbreviate the maximum, right, of Sn. Sorry, it should be an I up. What is that? Sorry, maximum Si, right?
Yes, Si.
Sorry.
Abbreviate the maximum over the SIs by AN, right? Then we have our norming constant, the square, that's the standard deviation of the SN, right? That is this term, which we saw at various instances in Alan's lecture, right? And we abbreviate it for the moment by C sub n, right? That's the norming constant. And recall that the rescaled paths were just obtained by speeding up the time. For instance, the SN1 is S sub n, and rescaled, right? So that's good to know. And maybe the more important thing, right? This is important, right? The maximum of the SNT, where t is between 0 and 1, this is just the rescaled AN, right? AN divided by CN, right? We have this in mind, right? And now the lemma 4.1 says that there exists a constant C0 such that for each epsilon, there exists an N0 depending on epsilon, such that for n larger than epsilon, we have this estimate, right? That's this lemma 4.1. And now you look at the AN, right? And by some nice analysis involving the FKG inequality, right? You can pin down the distribution of the AN somehow, and you define a sequence alpha n, depending on epsilon, right? That somehow you look into the distributional range of the ANs, and you manage to show the existence of a properly defined AN. That's specifically defined, and you obtain this inequality, right? This is already a sort of concentration thing, right? And then from there, in order to arrive at the assertion of your lemma, it suffices to show for this rescaled Rn, right? Imagine, keep in mind, we have this alpha n, which figures in this estimate, right? Here is where the alpha n figures. And then you divide alpha n actually, in fact, by the norming constant, but split off the C tilde. This does no harm. You maybe could have, I don't know, have split also the C tilde off here, but then what you have to show is, in fact, boundedness of this Rn. So in order to make it more picturesque, you want that this alpha n lives on the right scale, right? Here is the AN, which is a large thing, right? If you rescale the AN, then you are to units of 1. And the alpha n, if you rescale it, then you come to the Rn, and the claim is that the Rn should be bounded, right? That's the thing, right? You have to prove star, and now by acute argument, building on proposition 3, building on the finite dimensional convergence of the scaled walks towards the fractional Brownian motion, you can show this, this fact. For any k, there exists an n0, so that for epsilon small enough and large n, we have this inequality, right? R evaluated at a multiple of n, k times n, is smaller or equal than what is written here. And probably I hand over to Jan Lucas here.
Maybe one should say at this point that somehow a recursion inequality.
Yeah, a recursive inequality.
Yes,
right?
It's just a recursive inequality. And one could believe that one gets the boundedness because of what? If you take a large k that's small, so Rkn is nothing else than something really small times Rn plus, constants. not interesting constants, okay? So one could believe that slowly than linear, it could be bounded. And so what we should show is the supremum of the Rn is bounded. And what Alan and Scott said is the following: just fix a k high enough so the 2k to the power of -1/2 minus alpha is smaller than 1. So this thing is smaller than 1. And what we then find is that the lim sub of the Rms along the subsequence k times n is at most this thing, a constant. Okay, I would say if I talk to someone and tell them that, he would believe me. And I first believed you, and then I didn't really find the argument. And then was this evening, Anton and me and his wife, we go get biking. And when we were dining, we thought, okay, we have it. Everything is true. And I got home and I calculated carefully and wrote this email. No, everything what I did was a mistake. Okay, but get on. Why isn't that true? It's not so easy to see that. We have a little counterexample prepared. So, okay, we fix this k high enough such that 2k to the power of -1/2 minus alpha is smaller than 1. And what we do now is the following. We just define an Rn satisfying the recurrence inequality we have. So just take the recurrence inequality and make it an equality, and say Rn is this times Rn divided by k plus our constant. Okay, our constant depends on k. And of course, we only do that if k divides n. What we can do with the other parts of the sequence is just set it Sn for a sequence, a positive sequence whose restriction on the prime numbers is unbounded. Okay, there are infinitely many prime numbers, so for infinitely many n, we have a subsequence that's not bounded. And I think the argument is somehow destroyed, because the restriction of Rn to the prime numbers is then also unbounded. But I believe there could be an idea how to fix that. And I believe Anton wanted to say something.
Well, probably here, right? Your original difficulty, Jan Lucas, was that here it's claimed that
that these linear subsequences are.
And I mean the recursion which one has here, right, is for k times n.
So one gets is that r k to the power of n, or multiply by some small m. Right. That is bounded, because you just put in the recurrence inequality and get that it's bounded. It's just a geometric series. I'm happy with that. So what you get is that for all k greater or equal to 0, rk to the power of n, that is bounded.
So it's fine along powers of k, right? But it's not. I mean, with the multiples of all numbers. I mean, yes. That's you can always start afresh with some prime and make things.
You have infinitely many of those sequences, and they get far away from another. And then you can do some analysis, and I try to do that. What a sequence has to satisfy, what a subsequence has to satisfy, so that the boundedness of the subsequence would give us the boundedness of the whole sequence. And one tool I had in mind is what Alan and Scott said. What we know is that the difference of the alpha m's is just, or is at most the difference of the indexes. And yeah, so that are two different scales. That is a linear scaling, and what you need for the boundedness of k is somehow at least polynomial or something. Yeah, okay. I believe the counterexample is somehow clear, because yeah, the recursion inequality is satisfied per definition. And what we have, what one could do, maybe, is just use some more model-specific things about Rn to conclude the boundedness. And
Right.
that's the thing we put a price on.
Right, because actually the Rn is specific, right? You define the alpha n in terms of the distribution of the an, right? The alpha n is well defined, but then as far as we understood from the quoted paragraph, right? It's a sort of abstract argument here, right? It's that you say, because we have this, what's here, the 7, right? Because we have here this
Recursion inequality?
recursive inequality, from that we get the boundedness of the Rn, right? Everywhere, uniform, the boundedness of the Rn. And maybe one has to invoke here some additional knowledge about what the Rn really is, right? And that's what is the point? What is our point here, right?
And is it somehow fairly local change? That the additional information at some rough level could be described as being somehow to do with the change in the alpha or the R values when you just change the index n fairly locally, or would you say? I mean, if you take the basic your equation 7, and if you knew that at RKN plus, you know,
yeah, that's what I think. What wasn't quite working. The problem seems that you only get boundedness along maybe the shifted power sequence, the subsequences of the natural numbers, and not about these along these linear subsequences. I believe, however you use 7, you only get the boundedness on some power sequences in the natural numbers. K to the power of n, and multiples of this for each k. But each of these sequences, at least the sequences starting at prime numbers or at the powers of prime numbers, they can be
they are not under control, right?
Yeah.
Whenever you start at a prime number, right, then you cannot compare it to something smaller, right?
Yeah.
So you can let it grow along prime numbers arbitrarily. I mean, that's the core of the observation. And of course, it might be that from the mere what's formulated here, we are missing something, and I mean that would be interesting to discuss. But on the other hand, it's not tragic at all, because there is this other route. Right?
I believe also your lemma for 2 is true. So nothing is really wrong.
Yeah, I mean for 2, that's the next thing. That's fine.
I think we were a little bit slapdash and rushed in certain moments, and we certainly appreciate all the effort you put in to clarify these things, and both in terms of pointing out this counterexample, but perhaps just as importantly in terms of developing a different perspective, which could perhaps be relevant if the question arises of studying convergence of other models for fractional Brownian motion.
Sure. I mean, that's precisely, I mean, now we are over time, right? That would have been precisely the point in this part 5, right?
What we can do, I don't know if you're around on Thursday.
Yeah, sure. I mean, if that does not destroy any other plans of how you want to proceed,
Frankly, at practical level, it's
to,
rather helpful because I actually have a lot of things to do this week, and so I'm struggling to prepare
Yeah,
class. In
with
fact,
a lot of pleasure. With a lot
yes.
of pleasure. Then we jump in on Thursday at the beginning, right? Right away, or
why don't we pick it up on Thursday with this? I'm vaguely aware of this paper, and it would be interesting to recall it, this ancestral process
right.
paper.
Yes.
And then we can have a bit of a debate about that. And then what we can also do is maybe, there's a couple of other things. I don't know, I was going to suggest Adam or Jake, are you still around? Would you be, you made a bit more progress on the cookie collector. Would that be something you might want to talk about on Thursday? Give us an overview.
Be also very interesting for us. Yes.
Yeah, to be frank, I'm not sure how related it ended up being to fractional Brownian motion at all, but
well,
as an interesting thing in its own right, we could talk about it.
It does have connections, though. I mean, like the class is about these kind of random devil staircases, and the model has Brownian local time, so there's interesting connections there. And then I'd like to mention some open problems on Thursday related to, indeed, the voter model is an example of something that I think could be explored. I don't know, do you have any reactions, Scott? Our slightly slapdash writing up has been exposed years later. I don't know if you have any anything you want to put in. I think.
Let this be a lesson to everyone. Write your papers carefully. Oh, this is great. Very nice. It was very fun to hear what you guys have done, and very impressive.
Thank you. And let me emphasize that if there hadn't been this this little thing, right, which is curable anyway, right, we would not have had this interaction with you probably, right? We would everybody would have gone one's way, right? And so I think this is also a lesson to be quite happy with imperfectionism, right? Because so many other nice things come out of that.
I mean,
Okay, sorry, I got it backwards. You should make mistakes in your papers.
In a very expert way. I mean, one sees that you knew how the things have to go, right? And you did the right thing. You came up with this tightness criterion, right? And gave the right argument. But I mean, there is this little thing which maybe can be cured in its own right. That's where I put the, I have to say what, right? I mean, maybe some amount of.
Maybe there's just a little trick we missed when we calculated it, but. I mean, the whole
That could
idea
be a
is
direction for if anyone's interested in the class wants to pick up on it. It's a technical point, but it's not without interest if someone wants to pick up on that and perhaps chat with Jan Lucas and Anton and develop that to see if it's fixable or not. That
maybe even to confirm and to say, yeah, you were right, and this is indeed. But probably there is also some thought we are missing. Like, anyway.
Let me stop recording.